Welcome to a deep dive into the fascinating, and let's be honest, often head-scratching, world of renormalization. Now, if you're like most people, you might be thinking, renormal what?
Haha, it's definitely a mouthful.
But trust me, it's a concept that's worth wrapping our heads around. In the simplest terms, it's a mathematical technique used in quantum field theory.
Right, and it's all about dealing with something that physicists usually try to avoid at all costs. Infinities.
Infinities. In physics. That sounds, well, a bit messy.
It definitely puzzled physicists for decades. See, in quantum field theory, we're trying to understand the universe at its most basic level, like the tiniest particles and how they interact.
So we're talking about the quantum world where things get really weird.
Exactly. And when physicists started trying to calculate certain quantities in this theory, like the energy of a particle, they kept running into answers that were infinitely large.
Okay, so that doesn't sound good. I mean, how can something have infinite energy?
Right. It's like saying a grain of sand contains the energy of a million suns. It just doesn't make physical sense.
So how do they deal with this problem? Surely they didn't just sweep it under the rug.
No, they didn't. That's where renormalization comes in. It's a way of making sense of these infinities and getting finite results that we can actually test with experiments.
So it's like taking an equation that's gone completely bonkers and finding a way to tweak it until it spits out a sensible answer.
That's a good analogy. Renormalization doesn't make the infinities magically disappear, but it helps us manage them. It allows us to separate the physically relevant information from the parts that are blowing up to infinity.
I'm starting to get a glimpse of how useful this could be, but how does it actually work in practice?
Well, the basic idea is to redefine the parameters of the theory, like the mass and charge of a particle.
Wait a minute, are you saying the mass and charge of an electron, for example, are not actually constant?
That's exactly what I'm saying. It turns out that these properties, which we usually think of as fixed, actually depend on the energy scale at which we're observing them.
That's pretty mind-blowing.
It is. And the really cool thing is that this idea of renormalization actually leads to some incredibly accurate predictions that have been confirmed by experiments time and time again.
So it's not just a mathematical trick. It's a way of revealing a deeper truth about the universe.
Absolutely. And one of the most striking examples of this is the anomalous magnetic moment of the electron.
Okay, I think we need to break that down. What is a magnetic moment?
Right.
And what's so anomalous about it?
Okay, so imagine an electron spinning a tiny top.
Okay, I can picture that.
This spinning electric charge creates a magnetic field, just like a miniature bar magnet. And the strength of this magnetic field is what we call its magnetic moment.
So you're saying every electron is like a tiny little magnet. That's pretty cool.
It is. Now, classical physics predicts a specific value for the strength of this magnetic moment. But when physicists tried to calculate it using quantum electrodynamics, or QED, they found a small discrepancy.
So the quantum world throws a wrench into things again.
You got it. And this discrepancy, known as the anomalous magnetic moment, was a real puzzle for a while. But guess what came to the rescue?
I think I can guess. Renormalization.
Bingo. By carefully taking into account all the virtual particles popping in and out of existence around the electron, physicists were able to calculate the anomalous magnetic moment with incredible precision.
And did it match the experimental measurements?
It did. And the agreement between theory and experiment is one of the most precise in all of science. It's a stunning confirmation of the power of renormalization.
So renormalization isn't just some esoteric concept. It's a crucial tool that has revolutionized our understanding of particle physics.
Absolutely. And what's even more fascinating is that it hints at the possibility that our current theories of physics, like the Standard Model, might just be effective theories.
Hold on, effective theories. What does that even mean?
Well, think of it like this. Imagine you have a really detailed map of a city, one that shows every street and building.
Okay, got it.
That map would be perfect for getting around town, right? But what if you wanted to travel to another country or even another continent?
You'd probably need a different kind of map. One that shows the bigger picture, even if it doesn't have all the details of every little street.
Exactly. And that's kind of what we mean by effective theories. They're like maps that work really well at a certain scale or energy level, but they might not be the whole story at a more fundamental level.
So are you saying that the Standard Model, which describes all the known particles and forces, except gravity, is like a detailed city map? It works great for explaining things at the energies we can currently observe, but might not be the ultimate theory of reality.
Precisely. Renormalization sort of hints at this. It suggests that as we go to higher and higher energies, like those that existed in the very early universe, the structure of the universe itself might change. The particles and forces we're familiar with could merge and transform into something entirely different.
Wow, that's a pretty radical idea. Are you saying the standard model is wrong?
Not necessarily wrong, but perhaps incomplete. Think about Newtonian mechanics, for instance. It's still a pretty good way to describe motion at everyday speeds, but it breaks down when you approach the speed of light.
Ah, so Einstein's theory of relativity gives us a more complete picture, right? It includes Newtonian mechanics as a special case.
Exactly. And renormalization hints that something similar could be happening with the standard model. It might be a low-energy approximation of a more fundamental theory, one that governs the universe at incredibly high energies, a theory that we haven't discovered yet.
So that means physicists are on a quest to find this more fundamental theory, this so-called theory of everything, that would explain everything from the tiniest particles to the largest structures in the universe. A theory that would include gravity.
That's the holy grail of modern physics, you could say. And renormalization gives us some pretty tantalizing clues. It suggests that the very properties of the universe itself might change at vastly different energy scales. It points to a deeper reality beyond our current understanding.
This is starting to get pretty philosophical. So you're saying the very nature of reality might be fluid, changing depending on the energy at which we observe it.
It's a pretty mind-bending concept, that's for sure. Renormalization forces us to really question our assumptions about what's fundamental and what's emergent. It tells us that the universe is far stranger and more wondrous than we could have ever imagined.
I can see why physicists get so excited about renormalization. It's not just a way to fix infinities. It's a powerful tool that points the way to a deeper understanding of reality itself.
Exactly. And it all started with those pesky infinities. It's amazing how something that initially seemed like a problem turned out to be such a profound insight.
It's like finding a hidden doorway in a seemingly ordinary wall, a doorway that leads to a whole new realm of understanding.
You got it. Renormalization is kind of like that hidden doorway, a doorway that leads to a realm of physics beyond our wildest dreams.
I'm definitely eager to see where this journey takes us. But before we get too carried away with these grand ideas, maybe it would be helpful to ground our discussion with some concrete examples. We've talked a lot about the theory, but how does renormalization actually work in practice?
You're right. Let's bring things down to earth a bit and look at some real-world applications. It's time to see this seemingly abstract technique in action.
Okay, I'm ready to see how renormalization goes from being this theoretical concept to something that actually helps us understand and predict physical phenomena.
All right, let's start with one of the most striking successes of renormalization: the behavior of the strong nuclear force.
Okay, the strong force. Remind me what that's all about.
Well, the strong force is one of the four fundamental forces of nature, right? It's the force that's responsible for binding protons and neutrons together in the nucleus of an atom.
Ah, right. So it's basically what holds the very heart of matter together. Pretty important stuff.
Absolutely. And it turns out that the strong force has a very, shall we say, peculiar property. It actually gets weaker at very short distances and stronger at larger distances.
That's counterintuitive. I mean, usually forces get weaker as things get farther apart, don't they?
Yeah, you'd think so. It's like a rubber band that gets tighter as you stretch it. It just doesn't seem to make sense.
So this strange behavior has a name, I assume.
It does. It's called asymptotic freedom, and it was a major head-scratcher for physicists for a long time.
I have a feeling I know what's coming next. Renormalization comes to the rescue.
You know it. Renormalization was absolutely crucial for understanding this asymptotic freedom and making accurate predictions about how the strong force behaves at different energy scales.
So renormalization helped explain why the strong force acts so differently at short and long distances.
Exactly. And this understanding has had huge implications for our understanding of nuclear physics, particle physics, and even cosmology.
It's pretty amazing. It seems like renormalization is popping up everywhere we look. It's like a universal key that unlocks all these deeper secrets about the universe.
It's definitely one of the most powerful tools we have in physics, and its implications go way beyond just particle physics.
Okay, I'm intrigued. Tell me more about these wider applications of renormalization.
Sure. For example, it's been used to understand phase transitions in condensed matter physics. Things like the transition from a liquid to a gas, or from a non-magnetic material to a magnetic one.
So renormalization isn't just about high-energy particles and fundamental forces. It also helps us understand everyday phenomena.
Exactly. It's a surprisingly versatile concept. It's like a universal language that we can use to describe all sorts of physical systems at different scales and energies.
This deep dive has been incredibly eye-opening. We've gone from these pesky infinities to the profound implications of renormalization for our understanding of the universe.
It's been a whirlwind tour of one of the most fascinating ideas in all of physics.
It really has. But as we wrap up this part, I'm left with one big question. What are the frontiers of renormalization? Where is this field headed in the future?
That's a great question to ponder. One of the most exciting avenues is the search for a theory of quantum gravity, a theory that unites general relativity and quantum mechanics.
Ah, the elusive theory of everything. The one physicists have been chasing for decades.
You got it. And some physicists believe that renormalization might hold the key to finally unifying these two theories.
So the quest to understand the universe at its most fundamental level could lead us to some even deeper insights into renormalization itself.
It's a tantalizing possibility. Another exciting frontier is figuring out how to apply renormalization to other areas of physics beyond particle physics and condensed matter physics. Researchers are exploring its potential in fields like cosmology, astrophysics, even biology.
So the journey of renormalization continues.
It most certainly does. There's still so much we don't know, but renormalization gives us a powerful framework for exploring the unknown and pushing the boundaries of our understanding.
Well, I think we've covered a lot of ground in this deep dive. We've gone from the basics of renormalization to its role in potentially unifying the forces of nature.
It's been quite a journey, and I hope you've enjoyed it.
Yeah, it's really been fascinating to explore all of this with you. We've seen how renormalization helps us tame those infinities in quantum field theory, and how it's given us a deeper understanding of how particles actually interact.
And we even touched on how it's being applied in other areas of physics, like in condensed matter physics, where it's shedding light on things like phase transitions.
It's pretty mind-blowing when you think about it, how something that came about from trying to deal with these nonsensical infinities has become this incredibly powerful tool for understanding the universe.
It really speaks to the ingenuity and creativity of physicists.
Absolutely. They took a problem that seemed like a dead end and turned it into this profound insight. So as we wrap up this deep dive, I'm curious, what's next for renormalization? What are some of the big unanswered questions that physicists are still grappling with?
That's a great question. One of the biggest challenges right now is figuring out how to apply renormalization to gravity.
Ah, yes, gravity. That's the one force that has stubbornly resisted being unified with the other forces in the standard model.
Exactly. And it turns out that applying renormalization to gravity is a lot trickier than applying it to the other forces.
Is that because gravity is so much weaker than the other forces?
Well, that's part of it, but it's more complicated than that. See, in quantum field theory, we describe forces in terms of particles. Like, the electromagnetic force is carried by photons, the strong force is carried by gluons.
Right. So what particle carries gravity?
Well, that's the million-dollar question. We haven't actually discovered a particle that carries gravity yet. Physicists have proposed this hypothetical particle called the graviton, but we've never actually observed it.
So without a graviton to work with, it's hard to apply the usual renormalization techniques to gravity.
Exactly. The math of renormalization kind of depends on having a well-defined particle that mediates the force. Without that, we're a bit stuck.
That sounds like a pretty formidable challenge. Are there any promising avenues of research that might lead to a breakthrough?
There are. One of the most promising is string theory, which tries to bring all the forces of nature together, including gravity, by describing them in terms of these tiny vibrating strings.
Oh yeah, string theory. That's one of those mind-blowing theories that aims to explain everything in the universe, right?
It is. And the amazing thing about string theory is that it naturally incorporates gravity. The graviton just pops out as a specific vibration of these strings.
So could string theory be the key to finally renormalizing gravity?
It's definitely a possibility. Of course, string theory is a very complex and mathematically challenging theory, and we're still a long way from fully understanding it.
But it's an area of active research, and there's hope that it might lead to a breakthrough in our understanding of gravity and how it fits in with the other forces.
Absolutely. Another promising approach is loop quantum gravity, which offers a different way of trying to unify gravity with quantum mechanics.
Loop quantum gravity. How's that different from string theory?
Well, instead of thinking about gravity in terms of particles, loop quantum gravity describes it in terms of these loops of space and time.
Loops of space and time. Wow, that sounds even more mind-blowing than string theory.
It is pretty wild, and it's still a very speculative theory, but it has some really intriguing features that make it worth exploring.
So it seems like the search for a theory of quantum gravity is still very much ongoing, and renormalization is likely to play a big part in that search.
It certainly is, and who knows what other surprises renormalization might have in store for us as we continue to delve deeper into the mysteries of the universe.
Well, I think we've covered an incredible amount of ground in this deep dive. We've gone from the basics of renormalization to its potential role in unifying the forces of nature. It's really been an amazing journey.
I agree. It's pretty incredible how a concept that was initially developed to deal with infinities has given us such profound insights into the very fabric of reality.
It really is a testament to the power of human curiosity and our desire to understand the universe around us. And on that note, I think it's time to bring our deep dive into the world of renormalization to a close. Thank you so much for joining us on this incredible adventure.
It's been a pleasure exploring these mind-blowing ideas with you. Keep questioning, keep exploring, and until next time, keep wondering about the mysteries of the cosmos.